Uh-oh. That's not right. Welcome back to Joe's Computer Museum. Well, it seems my Apple II over here has got a little bit of a problem. It's got that old power supply reset of death issue that basically means there's a dead short somewhere in the system. Well, I've traced it down to exactly the device that's causing the problem inside the system, so let's check that out. What's causing that is this thing right here. This is a super serial clone card that came with one of my other Apple IIs. That I put in this other one here for testing. And yeah, when you put this in any Apple II that I got, it just causes the power supply to go beep, 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 and do its reset of death. So I decided to dig in to see what was going on with this and see if we can figure out how we can repair this card and maybe save it so that one more of our precious 8-bit pieces of equipment here is saved from going to the trash heap. So I was just looking around real quick, and I noticed something actually quite glaringly obvious. See if I can get this in here. If we take a look at this guy right here, this capacitor is very obviously just destroyed. And if we peel it back a little bit, you can even see some discoloration here on the side of this socket. So yeah, this guy's probably just gone dead short and is basically just shorting between 5 volts and ground. You know, you drop between 5 and ground, and you're going to pull so much current to the supply, it's just going to freak out and go into protection mode. So yeah, it stands to reason we can test this out, test this theory, and see how we figure that out. So this is a decoupling capacitor, like I said. A brief description of what that means. A decoupling capacitor, I like to think of it as basically a little bit of electrical protection for digital circuits. What it does is when a logic circuit is doing some heavy switching, it can pull extra current from the 5-volt line. That extra current can cause other parts of the circuit to go out of spec. And potentially oscillate, do warbly, weird things and stuff like that. So one of the ways you protect that is by putting this in here between 5 volt and ground. When you do that, it'll charge up to its capacitance, and it'll hold that capacitance until the value on the power rail or the voltage on the power rail drops a little bit, and then it'll dump its energy onto the power rail to kind of buffer to bring it back up. And that helps, keep everything within spec. That's my pedestrian explanation. Electronics folks out there, pardon me if none of my terminology is right. So operationally, this isn't actually required to operate in this machine. We could just cut that out, and it would probably work fine. But in the spirit of proper operation, I think all we really need to do to fix this is to replace that. However, because this is a dead short, and it is dead shorting between the 2 power pins of one of these circuits here, we should probably test that circuit as well. Testing this guy is easy. You just cut the pin and see if the shorting stops. This is a little bit trickier. So what is this chip right here? Well, this is a 74 LS279. Basically, it's a quad SR flip-flop. Quad meaning it's got 4 discrete flip-flop circuits in it. And a flip-flop meaning, how can I describe a flip-flop? Basically, it's a digital switch that when it receives an input, it will turn on, and then when it receives the input again, it turns off. It flips, flops back and forth. So you can basically use it as a single bit, or in the case of the SR flip-flop, as a multi-bit input trigger that can turn certain things on and off in the system. SR in this specific case means it has 2 inputs, S for set and R for reset. So basically these lines, as you can tell by the invert, they're triggered by bringing them low. So these are usually left high at 5 volts. And then when they receive a low pulse, a 0-volt pulse, or basically just an interruption in current, on the S line, it sets it and turns the switch on. Then to reset it and turn the switch back off, you send a pulse to R, and that turns it back off. So all we really need to do to test this is put the design in circuit and see if it operates. But the best way we can do that is by effectively putting together a test jig, and that is what this guy is right here. So basically we just put our 279 right in here, and it connects to all the proper input and output pins. And then it has a series of switches. Each pair of switches is the S and R, they're set and reset for each one of those quad latches or quad those four flip-flops. And then those, as you can see, we have the outputs of those tied to these LEDs. So as I go through these, I should be able to turn each of these LEDs on and off in sequence. So without further ado, let's just yank the chip out, plug it in there, and see if it's good. We'll see if that capacitor really did fry anything. So what I like to do this is I have a little Swiss Army knife type of thing that fits perfectly under these little chips. So basically you can just go in there and wiggle it a little bit. Pops right out like a champ. So let's get my test jig in here and get the chip in the test jig and make sure I have things oriented correctly. Right like that. Great. So let's get our power and get this in here. And there we are. And then we turn it on. So, as default, it does nothing because none of the switches have been set or reset. So all we have to do is go through these SRs and see if these light up correctly. So, set, reset, set, reset, set, oops, set. Ooh, something's not going on right with that one. Maybe my LED's loose. Reset, set, reset, set. Yep, okay. And then set, reset. Wait a second. So we set this one, then reset this one with that one turned on. Set this one, reset. That's bad logic chip. Glad we put together the jig to test it. So let's go ahead and pop this chip out, and I actually happen to have a replacement chip right here. We'll pop that into the test jig and we'll show you how that's actually supposed to work. So we'll turn the power off here. We'll get this chip on out of there. And we'll put this one in. Different brand, same chip though. Power that one up. And first off, right off the bat, you can see that this guy, when I power it up, the lights actually turn on when I power it up. So that's different from what the other chip was doing. So let's just go through these: set, reset, set, reset, set, reset, set, reset, and set, reset, set, reset, set, reset, set, reset. So they are working. 1, 2, 3, 4, 5, 6, 7, 8. So that means this chip is correct. So we can go ahead and power that off. So now we have an understanding how this chip is supposed to work and how it's supposed to get its inputs. And because we have this control in here, the scientific control if you want to call it, we know how it's supposed to work compared to how this chip is working, so we know that this chip really is bad. So we do have to go ahead and replace that. So now all we got to do is dig in here into this this clone card, the super serial clone, and replace everything and see if we can make some magic happen. So let's do that. I have my soldering iron all here at the ready, and my solder wick and everything. So this is the capacitor we have to remove. Now I do have an original actual super serial card here showing this capacitor. It is capacitor C5. It's hard to read, but it's this one actually says it on here if we can look at it. It's a 0.01 mic, also known as a 100 nanofarad, which I just so happen to have some of, so we can just go ahead and put that in there. So we need to get this out of here. And so that's here. So if we flip that over, that's going to be these two points right here. As a matter of fact, if I look really closely, it's kind of hard to see for you guys maybe, but let's see if we can focus on that. That solder joint in there is not very good either. So it's possible that there might have been this bad joint might have caused some current flow issues or something that caused this to fail fail prematurely. I can't talk today. Or who knows what. So we'll just go ahead and see if I can't get that out of there. So theoretically, I should just be able to heat that up and put this knife below it just to give it a little bit of tension, and it should pop right out. So let's actually focus so you can see what I'm doing here. See if we can get that out. Now, granted, I might need to reflow a little solder on this to get it to flow nicely. Let's see here. Yep. And if we look on the other side, that popped out already. So, reflow a little bit of this on that one. See if we can't get that out. It's a little tricky trying to pry these things out. Let me see if I've got my magic pliers. Hold on. My magic pliers, my little angled nose pliers allow me to get in here pretty easy and get an angle on this, put some tension on this, and maybe get this out of here. And there it is. It's out. So all we got to do now is, this is going to seem counterintuitive, we are going to reflow a little more solder on there to make sure that the solder that's in there flows really nicely. That's nice and easy flow solder. Now we get our solder wick, this stuff right here, and we just suck those holes right out. We'll see if we can do that. Stuff conducts heat really well, so I'm going to use my pliers to hold it down. If I can get it in there. There we go. Don't want to burn myself, you know. Bad mojo. Now, I'm not the best solderer, so this might take me a little while to get all this solder out of here. Oh, that one's clear. That's good. Let's try this one. Not quite yet. This one just doesn't want to get down in there and get that solder out. Let's see if we can get it from the other side. Doobie doobie doo, be doobie doobie, doobie doobie doo, doo 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 doo, doo 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 doo. Nope, it's being belligerent. I may have to put a jump cut in here while I get this out of here. As I said, I'm admittedly the worst solderer in the world, so if I need to jump, I will jump and be back in a minute. Oh, and we're back, and I got it out. I actually wasn't gone that long. So now we just need to get this new one in here. Looks like we might have to bend these leads out a little bit to get that in, but that's okay. That should not be a problem, because we have, again, our trusty, awesome pliers I like to use for this kind of thing. Okay. Let's see if we can't get that in there. Now this doesn't have any polarity on it, so it doesn't matter which way it goes. Just kind of shove it in the hole. And there we are. So now all we have to do is flow some solder on that, and it should be good to go. Let's see here. Here's one. There's the other. Not quite enough in there. There we go. Good. So we have the capacitor replaced. New capacitor in there. It's not quite in there even, so I'm going to see if I can even that up a little bit. There we go. That's better. All right. Just clip the extra long leads off of here. We don't need those on there anymore. Leads are cropped short. Capacitor replaced. Good as new. So, let's see if we can't take a super close look at this guy. See how close I can get into Mr. Camera. Yeah, I'm just outside the focus range. But yeah, that is just toasty. 104 meaning a 100 nanofarad. And it's just got this nasty strip down the middle of it. Now, let's actually test some circuit theory here. So, you know, capacitors don't really conduct electricity. They charge up, then they release it. And we can actually show you that by getting out another 100 nanofarad. 100 nanofarad. And doing a little continuity test on that. Focus! There you are. So if we do a little test on this, continuity mode. So if I put this across this, I should receive no continuity whatsoever. Nothing at all. And I don't, because it charges up then releases. So it doesn't really have continuity. But this, I think, is short. It's just dead short. So let's check it. Yep, sure is. So, you know, the little brown mark wasn't telling enough. You know, it definitely is shorted out. Always good to empirically test things instead of just assuming them, you know. So let's go ahead and get things put back away here so I don't lose them. So now all we have to do with this card is basically get the new chip in it, which is this guy right here. We pop that chip in, and there you are. That card should be repaired. Now let's take a look at it over here in the Apple II and see what happens. Now we test it out. We've got the card we just repaired in the Apple II. We have everything hooked up. So let's flip the switch and see if we get infinite resets or if we get an Apple II prompt. It's beeped. Screen's warming up. And there we go. Looks like we have a successful repair. Well, that was a fun little project. These old 8-bit computers can be a little tricky to diagnose and repair, but it just goes to show, with a little bit of patience, some research, and the data sheets on hand, you can fix just about anything. Well, that's all for today's episode. While you're here, check out some of my other videos, and remember, 8 bits are all you need.